Hello and welcome. On the slide you see examples from YouTube videos I posted 12 years ago. At that time I highlighted the importance of the golden mean and that it is the building type of nature. The top left picture shows a rive tube with the asymmetrical arranged primary of the bipolar Tesla coil in the back. The short side is connected to the right electrode of the tube and the long side is connected to the left side. The power requirement is much lower and achieve at 5 volt input already a very large glow. It is also capacitive coupled, as direct connection to the rive tube did prove very difficult with a lot of power consumption and very low plasma generation. In the middle you see my performance chart of the large bipolar Tesla coil. It is a COP comparison chart between symmetrical blue and asymmetrical red line. Important to note is that the resonance frequency of this coil is around 300 kHz. However, the highest output for the asymmetrical side is 44 kHz. Good to see the very large gap between both primary coil arrangements. The top right picture is the Fibonacci series. It is the result of the golden mean and part of the fractals picture below. We find everywhere, which is the building matrix in the universe. So in today's video I will use a half-bridge amplifier, replicate what we have done the last time. The previous video left a couple of questions open. As you must understand, this is fundamental knowledge before you go and design anything, and I mean anything, not only electronics and power systems. It was mentioned that things can be understood when the schematic is presented. I beg to differ because there have been so many schematics and patterns presented, but nobody was ever able to replicate. I must go even so far that I say that printed circuit boards I provided do not function if someone else is soldering the correct components on them. There are not only many variants and errors you can produce. Nevertheless, I'm happy to present you the schematics for today in a SPICE simulation. All the phenomena we register are not be able to be simulated because the algorithm does not allow for such variations. The component values are in fact correct for your design. Here is the SPICE simulation. So here you see the diagram for the schematic. So the only difference we have, I did not put the impedance transformer in here to account for the impedance difference between the output side and the input side. So the step down impedance transformer. So that it can vary depending on what kind of circuitry you use. So I left that out. That's something you need to investigate on your own. So this is a driver. The driver allows us here, it has two output stages. One is non-inverted, one is inverted, goes to each individual one. They do not shorten. Reason being why when they are running at the same time they do not shorten is the same way as with my zero voltage switching device. Technically that is two C-class amplifiers together getting triggered by the independent wave at the same time. Yes, but no, not at the same time. Because you have always a voltage drop and you have a time when the driver becomes active, which is 4.5 volt. That means if you go below 4.5 volt, it switches the MOSFET off, and if you get above 4.5 volt, it switches it on. So we have technically a window of 9 volt where the sine wave goes up and down, which means we have a space, a time space in between, a delay in between, which allows for a proper functionality without shortening the circuit. The turn ratio is, as I said, 300 turns, gauge 18 or 1 millimeter on both sides for the primaries. And on the output side, we have 550 turns, 7 times 0.2 millimeter Huger wire. It cannot carry that much, but it has a lower skin effect compared to solid wires. 4.4 nanofarad, they are creating an LCR circuit with the virtual ground connection via 7P. So technically it is not connected to ground, but because if you put it on a table and you measure your coil, you have always a ground connection if you want it or not, and that has an effect on the frequency, and because it's simulation we have to put it to ground. So we're using sine wave 15.5 kilohertz, and can show you quickly how that looks like here. If I use it with just generic MOSFETs, it looks like that. And if I go into then the FFT, which is then the spectrum analysis, we see that we have two plots here. If I go with one in here, that is the first one, that is a major one I have designed. It's here. Bring up the measurement here, so we have 15.6 kilohertz, and if we go to the second one, let's do that, we have 18.4 kilohertz on the second cursor. So that means we have a range between 15.6 and 18.4 kilohertz based on what I have defined in here. However, in the experiment you will see that we are a little bit lower in the frequency because I have optimized a little bit more. I can do that technically by changing here my value for the sine wave to that same value, and it should turn out, if you just change it to 15 kilohertz, let's do that for a second. Change it to 15 kilohertz, spot on, and I do then the simulation again. It makes a change, but I have to plot it again here. It will look like that. If I go in here, I need to bring over the measurement up here again. So that is one, bring one up here. What do we have? Yeah, 15.2, 14.8, these are the peak values, and I just go quick over here, don't need to add a second one. Yeah, we stay at our 18.4. So these are the values here. I make this one available. Technically they're available for my members if you want, but you can take that as it is here as well. But the SMICE model, if you want that, they are on my members website, available for basic members and full members. So we go over now to the demonstration table, and I show you my setup there. So on the table you see it's the same setup as we had it the last time, and you see my half bridge amplifier on the left side, and then below me of course is my my voltage meter, differential voltage meter, and the GoPro is staying in the middle. So I will run anyway with the GoPro now because I have the full set, also a camera which shows you the power requirements. So I will run that through with the GoPro now, and then I will continue with the explanation, or do that while I'm doing my run through with the GoPro. So you see it's the same layout as you saw before, with a couple of additional components. So we still have the same connectivity via this oscilloscope. Then I have my camera here, which is recording then the values here on this power supply. It can only produce, or it can only deliver 3 ampere to maximum of 30 volts. And here we have my signal generator, the differential probe, and here, as you can see here, they're both connected at the same time. I'm using currently non-inverted and inverted here, 2 individual chips on the board. Before I used a coil with sender tap. That is not required anymore. By using 2 chips of them, with inverted, non-inverted, it will just fine. I probably will build a new board where I have only 1 BNC connector in there. That would save component. Only 1 signal coming in is good enough. So we have currently only these 2 MOSFETs, the IRFP 140, and we go out in a normal way. And you see again my impedance transformer, because here I have very, very low impedance, and here I have high impedance, so it's the other way around. So we have to make sure that that is matching, and that's how it currently is. So I leave this camera here and I switch over now to the composition. See if this works. Yes, it works. So we have this at the moment. I have it already configured correctly to the right frequency, so we don't need to go to all the differences. I'm just run this one up for a brief second that you can see what we currently have. It should be around the same 180 to 200 milliampere as I see. So we have 200 milliampere currently. Let it run again. 186. So it's exactly the same as it was as the last time. So I keep it here. Let's see, we keep it here on the side. There's nothing connected currently. Should not show 641. Let's see if it has 345. Let's do it another time. There should not be any power here at all. Not sure if the GoPro makes any difference here. 509. Not sure where this comes now, but 168 I have it here. Okay. If I energize that up, now I have it already at 13.88 volt, and remember we had an output of 1 watt because it's 50 ohms sine wave into 10 volt peak to peak. Here we have now 13.88 volt. It is not 100% perfect with the energy distribution. It should only be 10 volt, but because of our mismatch of the impedance, we have to get higher in the voltage in order to achieve that. So if I put that up now here, so we are seeing a complete different picture. We have power requirement 1 watt, you can see that here, 1 watt, it shows exactly the same value, but we have far more output power and optimization. And I measure 58 ampere here, and if I go over to this side, a similar exercise we have done the last time. Let's see what it gets. 90 ampere. So we have a much higher value than we had before. Yes, you can go with the same exercise we have done before. Let's say here at the end, what does it say? 35, and here 31. So we don't need to go to the extra bits and pieces, but I want to demonstrate that it's really the adjustment. If I go further away, that's 228. Not sure if I achieve that again. If I go a little bit out, I'm gone. If I go closer in, I'm gone. It is really the ratio between these two alignments. See if I can get back to 228. I can get even to 231. More? No. 231. So what it demonstrates is the asymmetrical alignment of coils. This is an indicator, nothing else, because currently we are not running really a load here. We're not running really something which is consuming the power. It is circulating power in this coil and nothing else. I want to make really sure that we are not consuming any power here. However, it produces the circulating power in this coil, which we can measure, right? It's an indicator, nothing else. So for us to design something, we need to have at first a proof of concept, that's what it is, before we go to the next stage. And I don't want to go too much in many more details, because that should give you a good idea in which direction we need to go. So the next exercise will be with a different setup, but showing exactly the same principle and the same result. So that gives you a variation of different kind of combinations of what you can do. So still electrical system, we're not doing anything mechanical, still electrical system, but it applies to them. So if you have questions, please let me know, and I wait for more people voting on the poll, and I will come up with a different scenario for the next time to show you that that applies for that as well. Thank you.